This is the last lecture for this class, and it's going to go over multiple regression, which is in your last homework, and I think in your last in-class in-class lab assignment. So last week we went over simple regression, which was the idea of you had one independent variable and one dependent variable, and the p-values all still work, where it's below 0.05 then it's statistically significant, and if you have a z-score, a t statistic or an f statistic that's above plus or minus 1.96, then you know it's statistically significant. So the coefficient of multiple determination, or r squared, which is on your table and will be in your output, is a proportion of the variation in a dependent variable that explained by the several explanatory variables. It lies between 0 and 1. The higher it is, the more variation in y that has been explained. And typically you won't get a 1. You'll get something like 0.4, 0.3, 0.2, 0.01. And you can think of this number as, if it's 0.1 is the r squared, then you take it times 100, and so that gives you, you explain 10%. Your variables, independent variables, explain 10% of the variance in this model. So if you add another explanatory variable, will almost always raise the value of the r squared. So asking or adding more variables will increase the r squared. But you don't necessarily want to do that as a researcher, because you want to stick to the theory or the program evaluation that you're conducting or whatever, and you don't want to just add independent variables into your model. So there are some notations for simple and multiple correlation and regression. So on the left-hand side, you have simple or bivariate regression. So little r squared is coefficient of determination, whereas two or more variables, it's the same thing, but now it's capitalized r squared, coefficient of determination. B is the regression of coefficient, because you only have one independent variable. B1, B2 are partial regression coefficients, because now you have two or more independent variables. And R, correlation coefficient, because little r, because you only have one independent variable and one dependent variable. Whereas on the multiple regression, where you have two or more independent variables, you have r, y, x1, x2, etc., and multiple correlation coefficients. So partial regression coefficient measures the influence of the particular variable on the dependent variable, while the influence of all the other explanatory variables is held constant. And so, for example, we're going to have this where we're looking at welfare and homelessness. So in Chicago, during the 1930s, records were found that include amounts spent each month averaged over a period of years in the 1930s. The records include outlays covered the cost of providing accommodation and clothing, operating a soup kitchen, and dispensing medicines. This research also finds an explanatory variable of the number of people who were sleeping, roughly expressed as a percentage of a city's population homeless. So here is the equation. Welfare is the dependent variable, and we have the constant is 431, plus the slope is 848 times homeless. And because we only have one independent variable, this is a simple linear regression or bivariate analysis, we have a little r squared of 0.63, which is really high. 63% of the variance in the dependent variable is explained by homelessness. And t ratio is highly significant, so we know that this is statistically significant. So how would we interpret this? With a rise of $848 for every 1 unit increase in homelessness, we would see 848 plus $431 for welfare. So then on the second example, we have now multiple regression. So we find that the constant is negative 1,245, plus the slope is 260 times homeless, plus temperature is 1,910, and we have an r squared of 91, capital R squared. And so that means that 91% of the variance is explained by these two variables, homelessness and temperature. So this is much more improved from the 63% that we saw before by just adding one variable. And also, as you know, the capital R squared increased significantly, larger number, by just adding one variable of temperature. So we can calculate these things about how much welfare is going to be produced by the indicating homelessness as a value, numeric value, and temperature as a numeric value. So this slide basically suggests that the slope or the constant changed, the slopes from the two equations change, and by adding temperature, this accounts for a single regression model to a multiple regression model. So when the effective temperature is held constant, the partial regression coefficients show that benefit payments rise by only $260 for every 1 percentage point increase in homelessness. So what could you say about summer then? So you could say that homelessness would decline, right? The benefits from the welfare would decline because it doesn't increase as fast. But if in winter the temperature declines, so there would be more welfare payouts. So if we added food costs instead of temperature, and we had an R squared of 0.83, it goes down slightly, but we explain 83% of the variance by substituting temperature for food costs. So we also see that the constants change, the slope has changed, and what else might you see from these three different equations? So, is there a relationship among the explanatory variables, or is there a correlation? So we have homeless and temperature has a correlation of 0.73, and this would be strong, a strong correlation. This goes back to measure of association before spring break, where we had 0 to 0.1 is weak, etc. If we put homeless and temperature in the same regression, what would happen? Or why would we, or why not would we put homeless and temperature in the same equation? So we wouldn't, because they have high correlation, right? So you're basically saying the homeless and temperature are measuring in some way the same kind of stuff in your model, so you wouldn't put them in the same models for your multiple regression. So we'd have multicollinearity if we put temperature and homelessness in the same equation, because it was 0.73, right? Which means two or more explanatory variables are highly correlated with each other, and so we usually drop one of the explanatory models or run the models separately. So there's also on your output standardized beta coefficient, and this basically indicates what's the strongest variable to emphasize or affect the dependent variable. So it's a measure of the relative effect of each of the partial regression coefficients in comparable units. So the capitalized B on SPSS output, or the slope, right, is not standardized. So it's like apples and oranges comparing each other. The standardized beta coefficients are all apples or all oranges, so we're all comparing the same kind of stuff. It doesn't matter if they're positive or negative, it just matters what is the biggest number. So if the homeless and temperature standardized betas were 0.24 and 0.76 respectively, and homeless and food costs were 0.79 and 0.45 respectively. So in the first example, temperature is the most important variable in this model, and in the second model, right, where we have homeless and food costs, homelessness is the most important because it's 0.79. So adjusted coefficient, the multiple determination, or adjusted R squared, is equal to R squared corrected for the number of explanatory variables plus the intercept. So if temperature raised R squared from 0.63 to 0.91, and we look at the corrected adjusted R squared, then it's 0.888. So if the sample size is large, there's a little difference between R squared and adjusted R squared. But if the sample size is small, then there can be a lot of variance or differences between the R squared and adjusted R squared. And you want to report the adjusted R squared because it takes into account whether the sample size is big or large.